So we talked about something called Atwood's machine, and the idea is that you have two masses connected to each other by a rope that goes over a pulley. And for our purposes in this class, the pulley has no mass, no resistance to turning, although we will get to that problem where the pulley does have some resistance to turning. And what we were told in this problem is that there's a wood block on a wood table, and it has a mass M, and that there's some weight hanging down off the pulley that just gets it to slip. So the first thing we can do is actually find out what that mass can be. So we'll choose some axes, X and Y, and we'll set up the problem for just slipping. Now, what makes Atwood's machine an extra complication is that it has two different masses. So we really need two different free body diagrams. So let's call the mass hanging down big M. So for little m, I have gravity going downward, and I have the normal force going upward. And if it's just slipping, the force of friction has just been overcome, and so the force of friction is going to be mu s times that F normal. And there's a tension force that goes this way. Okay, so that's little m. What about big M? Well, big M's a little bit simpler. It just has this force of tension going upward, and it has a big mg going downward. So the aha moment here is realizing that these two forces have to be the same. They have to be the same tension. They're the same rope. And in fact, you can make arguments based on Newton's third law that those forces do indeed have to be the same. Be careful, though. They are not in the same direction, and that's what pulleys do. Pulleys change the direction of ropes. Pulleys change the direction of tension, not the amount. Okay, so what this means then is we have to write two separate sets of equations. And so for this case, I write the sum of the forces in the x direction and the sum of the forces in the y direction. And for this case, I do, well, I'm not going to write the x because there's clearly only y, but the sum of the forces in the y direction. And so in the y direction, I have the force of tension upward and gravity downward. And if it's just slipping, it's not accelerating yet, so that's 0. The sum of the forces in the x direction for the little mass, there's the force of tension in a positive direction, and then there's the force of friction, which I'm now going to write as mu s times the normal force in the other direction. Again, nobody's slipping in, so that has to be 0. In the y direction, I have the normal force and mg. Okay, so I really have three equations here. So the things I don't know are the force of tension, the normal force, and big M. So I have three equations and three unknowns. That's good. And one of them is the thing I care about, and the other two have to be eliminated. So this is just algebra now from here on out. But I might do some steps that look like this. So I'll take this first equation and show that the force of tension is equal to mu s times the normal force. Okay. So that means then that if I take this equation and plug it in down here, I get that the force of tension is equal to mg. And so the two of these together means that mu s times the normal force must be equal to mg. But I know from the third equation that the normal force is equal to mg. So when I plug that in here, I get mu s times little mg is equal to big M g. Oh, if I divide both sides by g, this says that the mass that makes this thing slip is going to be mu s times the mass of the block.